Hi guys, day 3, we are talking about dilations, and we're actually going to talk about dilating functions two different ways, vertically and horizontally. And we talk about it over 2 different days just because it really does get approached slightly differently. So the first part, it's got a little exploration for you. If we were doing this in class, I would give you guys some time to kind of work on it, but I'm going to walk you through it here. Hopefully you'll still be okay. It's asking you to create a table of values and graph the function f of x over just this little domain, right? So you have a spot down here to put the values so that you can record them and then put them right onto the graph over here. So let's take this first part, f of x, and just from 0 to 4. So if I slide up a little bit, you're going to have 0, 1, 2, 3, and 4. All right. Use your calculator. Save yourself some brain power. So if we type on in here x squared and then minus 4x and plus 3, go right over to that table of values. And hopefully you're looking at the values already. If not, you guys, you can always go to second window and you can have the table start at whatever value you want. So you can tell it to start at 0 right there. Just FYI. So at 0, I have 3. And then at 1 is 0, -1, 0, and 3. All right, take a moment and plot those values on your graph. All right, now because we are specifically graphing just over this domain, that means that you're going to have endpoints here. If I didn't give you a domain, then you would just graph it and you'd throw some arrows at the end, but I want endpoints because it's very specific. And then label this. Here's f of x. Just like the last few days, if you happen to have some different colors, if you got some highlighters, whatever you got rolling around in your desk there, that would be fabulous. So it says determine an equation for g of x that's going to equal 2 times f of x. Let's do some quick calculations here. So g of x is equal to 2 times f of x. So 2 times x squared minus 4x plus 3. And then you can distribute it and clean it up here. So this is going to be equal to g of x is 2x squared minus 8x plus 6, right? I'm going to circle that with my red pen because I'm going to use red on the graph here, all right? And it again says create a table and graph it from 0 to 4. Easy, all right? Let's do it. So let's go into this. I'm going to clear out what I had, and I'm going to type in 2x squared minus 8x plus 6. If at any point you need to pause the video so that you can graph everything and get it recorded appropriately, do it. Otherwise, keep on rolling with me here. So we're going to plot all these points. So we've got the point 0, 6. So 3, 6 is all the way at the top there. We still have 1, 0. We got 2, -2. And then back to 3, 0, and up to 4, and then 6. So doing the best you can, connecting the dots nice and pretty. All right, here is our g of x. All right, last one, you got one more function to go. I'm out of colors, but I got some highlighters, so I'll take advantage of that. Determine the graph for h of x. H of x is going to be equal to half of f of x. So we have half of x squared minus 4x plus 3. Don't be afraid of fractions. We can do this. So h of x is equal to 1/2 of x squared minus 2x plus, you can write it as 3 halves. You can make it 1.5. I don't care. Right? I'm going to use a yellow highlighter to kind of go over this guy. So into my calculator, switch it on up. We've got 1/2, or you can do 0.5 if that's easier to type in here. X squared minus 2x plus 3 halves. Right? And then go to your table and let's record those same values. So I'll record them in blue so that you can still read everything. But we should have 0, 1, 2, 3, 4, same domain. So we have 1.5, 0, -0.5, 0, and 1.5. All right, plot those on your graph. So we've got at 0, we're going up to 1.5. At 1, we're at 0. 2, we go down to a -0.5. 3, we're at 0. And at 4, we're back up to 1.5. All right. So when I draw this guy, There we go. We kind of end up with this. So here's my last graph. Middle one is my red, which is my g of x. And then my first one was my f of x. And I just realized I did not label the last one. So there is my h of x right there. And I'll go over it with my highlighter. All right. I like to color code things if you haven't figured that out yet. All right. It's asking you some values here. Let's answer them. What is the minimum value for each of the three functions graphed above? Something that you want to make sure you understand here. Minimum value is always referencing the lowest value on the graph, which is a y value. So when you look at these, you have three little pieces of parabolas. They're looking at the vertex point then. So the minimum point or the vertex for f came out to be -1. For the g function, it was -2. For the h function, it came down to -0.5. All right. So that is important to notice because it's going to help us understand the rule of what's going on here. Right? So it says, given the graph of each, or the graph of f of x, excuse me, and then the constant k, so the number that we multiplied it out front, the function k times f of x, where x was, or k was greater than 1, and then the function k times f of x, where k was between 0 and 1. What happened? Well, if we look, we never changed the domain. The domain stayed exactly the same. All the x values didn't vary at all. And yet the parabola still kind of showed that same piece. So first thing that we're showing here is that nothing happens to the x's, right? But what changed was the y values. So when we multiplied by a 2 out front, right, the y value for the minimum got doubled. When we multiplied by a half out front, the y value got chopped in half. So what you should be hopefully noticing, right, is that only the y values were affected. So I actually want to start by writing that down first. Only the y values are affected. And now what can you say about it? Well, when we multiplied by a 2, basically the graph completely like stretched out. When we multiplied by a half, the graph essentially gets squished or gets shrunk. So how do we say that nicely? Well, we can say that when k is bigger than 1, like when it was 2, that's referred to as a vertical stretch. And you can kind of loosely say, all right, the graph looks bigger because it's extended over more space. When k is multiplied by f of x and it's between 0 and 1, that's referred to as a vertical compression. So you're like smushing the graph in. It's like pinching it, right? Now, both of those are dilation, right? Dilation is just the changing of a size. So calling it a stretch versus a compression is just talking about how that size is changing. Sorry. All right. So what's the rule? Well, the rule is exactly the way it looks. If you do k times f of x, you're doing k times the y value. So all you have to do is just multiply the y value by whatever k is. So the rule here is to simply multiply the y value by k. So whatever the heck k is, if it's a half, if it's 2, if it's 7, whatever. So let's see if we can put that to work. Now down here, it says the quadratic function f of x has a turning point or a vertex point at -410. The quadratic y equals 1/2 of f of x minus 3 would have a turning point or a vertex point where? All right. Well, already we're throwing some stuff together here. So we have two different transformations happening. You have the 1/2 in front. You have a -3 at the end. So let's write down what each one's doing. So the 1/2, that's a value between 0 and 1. That is a vertical compression, which should make sense. You're essentially going to make it, half the height that it was. And then the -3, that's going to shift it down 3. So we're kind of combining things that we've talked about over the last few days. So let's take that point. Well, if I start with the point -410 and we have a vertical compression, like we just talked about, only the y value would be affected here. So you're going to multiply the y value times 1/2. So that would produce the point -4 and then 5. And now you're going to shift it down 3. So if I want to shift it down 3, we're going to subtract 3, but only from the y value because that's a vertical shift. So that x value didn't change at all. That -4 stays the same. 5 minus 3, that's going to land us at 2. So without actually seeing the graph, we can still transform where that vertex point or that turning point is going to be. So we squished it, so the y value got cut in half, and then we moved it down 3 units, so it went from 5 down to 2. All right, same type of thing with this one. If the point -312 lies on some graph y equals f of x, which of the following points has to lie on the graph of 3 times f of x? Again, try to remind yourself, f of x is the same thing as saying y. So if it says 3 times f of x, it's literally saying do 3 times the y value. So take the point, -312. Nothing's going to happen to the x. Just the y value is going to get multiplied by 3. So -3, and then this should be 36 right here. That's it. Done. All right. So vertical dilation only affects the vertical variable, which is the y variable. All right. Moving on to the back here, because there's only 2 pages of these notes. Not sure if you noticed that, but that's it. That's all there is. All right. On to the second page. It says the graph of f of x is shown. So that's this kind of squiggly guy over here. Consider the function y equals g of x given by g of x equals 2 times f of x and then -3. Okay. First of all, it's saying what 2 transformations are you going to do to f of x to produce g of x? So just based on the little equation here, you've got the 2, you've got the -3. I want you to think in terms of PEMDAS. So parentheses, exponents, multiplication, division, addition, subtraction. You have to approach it in the same order. So if it's 2 times f of x and then a -3, you got to take care of the multiplication transformation first and then the subtraction transformation second. And yes, the order matters. Occasionally you can flip-flop the order and get away with it, but it won't work in all cases. So for this first one, first transformation is the times 2. And what that is going to produce here is that we are going to vertically dilate or vertically stretch. And how you'd say this is by a factor of 2. So it's a vertical stretch by a factor of 2. What does that actually mean to you? Well, you're going to take all the y values and multiply them by 2. All right, that's what it's going to mean. The second thing is the -3. All right, well, what's the -3? If I have a -3 on the end, it's going to shift everything down 3 units. So we would say that's a translation or a shift down 3. Right? Again, up or down, that's a y value thing. So you're going to take the y values and you're going to subtract 3 from the y values. So this one, again, y value gets doubled, and then you subtract 3. We're not actually going to do anything to the x values. So the reason I bring this up is that if you're doing like a single transformation, like, hey, walk everything down 3, it might just be easy to go to the graph, move 3 down, plot the point. When you start doing a combination of things, it can be easy to get yourself a little bit confused by having too many steps going on at once. In that case, I actually think it's worth it to create a little table of values for the original function, and then a table of values once it's been transformed. So that would be the g of x function. And the values I would use off the graph would be those nice plotted corner points here. So like 1, 2, 3, 4. So this first one, -1, 2, 3, 4, 5, 6. And that's -2. This next one is -3, 2. This is 2, 1. And then the last one, we are over here at 5, 5. All right. The cool thing, nothing happens to the x's. So right now, all the x's, copy them down. So they stay -6, -3, 2, and 5. The only thing that's going to change here are the y values. So all these y values, we're going to calculate what they're going to turn into over here. So every y value, we're going to double it and then subtract 3. So if I take -2, here's some mental math time, double it, that becomes -4, subtract 3, that's -7. Play the game again, 2 times 2, +4, subtract 3, that's going to be 1. 1 times 2 is 2, subtract 3, that's -1. Last one, 5 times 2, that's 10, subtract 3, that'll give you 7. All right, now you can take all of these and come on over here and graph this. Okay, so you can go to -6 and then down to -7. So let's see, -4. All right, so we are down here at -3. We're up at 1. At 2, we are at -1. And at 5, we are at +7. All right, using my straight edge for sure on this guy. So connecting the dots. And now once you get a final answer, you may look at it and be like, yep, that's what I was expecting. Sometimes maybe not. So you might have to step back and think, like, does this fit what we said should be happening here? And I'll explain what I mean by that. We said that it should be vertically stretched. So if I think about the domain, or excuse me, the range that it had, it should be stretched out from there. It should be doubled, right? But then it also got shifted down 3 units. So it might look a little bit different than what you're expecting given that little shift there. But it should seem reasonable based on, what you knew was coming. All right, we're going to do a few more together and then call it quits. Number 4, if the quadratic function g of x has a y-intercept of 12, right? Y-intercept means it's the point 0, 12. It's where it's crossing the y-axis. Which of the following is true about the function h of x equals 3 times g of x minus 5, right? 3 times g of x means you're going to multiply the y value times 3. Minus 5 means you're then going to subtract 5 from it. All right, take that y value of 12, multiply it by 3. That'll give me 36. Subtract 5 from it. That's going to give me 31. Right there, that guy, that's choice 4. Does not affect the x value at all. All right, last one. Number 5, the function g of x is given by -5 times f of x plus 4. What 3 transformations have occurred to the graph of f of x to produce the graph of g of x? And specify the transformations and the order. The order meaning, think again about PEMDAS. That's going to tell you the order. All right. So 3 transformations. So 1, 2, 3. All right. Typically, numbers are what clue us into a transformation. So like the 5, the 4. The fact that it's a -5, I can actually break that apart and consider it 2 separate transformations. So I can make the -1 transformation, the 5 another, and then the 4. Now, does it matter whether you deal with the negative or the 5 first? Nope. But they both have to take place before the 4 because we're talking about multiplication before addition. So if we negate f of x, that is a reflection over the x-axis. So that's when we have this guy. Right? Then when you have the 5 out front, that is a vertical dilation or a vertical stretch. Call it either way, right? By a factor of 5. Right? So that's the 5 times f of x piece of it. And then the last part, the plus 4. The plus 4 means that we are shifting or we are translating, try to use that vocab, up 4 units, right? And so that's the whole piece of the f of x plus 4. So you don't have to show this part. You have to make sure that you understand this over here. That negative reflects it over x, the 5 dilates it vertically, and then the 4 shifts it up 4. All right, example 6, we're going to save that guy for the next time we're together in class. Don't forget to answer the post video question and have a good one.